Hi guys, in this video I will show you how to realize input-output instructions so that you can read characters from the keyboard and print characters on the terminal. I will also show you how to realize jump instructions. And for that I also have to explain you how the sequential execution of programs is realized on ULM with the so-called von Neumann cycle. In this video I will initially begin with a new minimalistic instruction set architecture with just a halt instruction, and then add more and more instructions to that for input, output, and jump instructions. And I will, most of all, use this opportunity to show you how powerful the build system for the ULM generator is. You see, I'm here in my Git clone of the ULM generator, and before I begin, I first want to check if something new was pushed by somebody to the repository, but you see the branch is up to date, so I don't have to pull new changes. And currently I have in this directory specifications for 2 instruction set architectures. I already built the computer architectures for them, and the executables are here in these 2 subdirectories. So now I can start with my new instruction set. I define them also in this directory. I call this architecture jump, and in jump I now create first this file variant.mk. So this is an empty file, and here you actually could specify certain options for this variant, which I don't need and don't specify. And then I'm specifying this new architecture here. And I will in the beginning just use this format with the typical op field with 8 bits unsigned. Although the signedness is here actually not needed. And this fields X, Y, and Z. And then in the beginning I just have this halt instruction, which of course uses this one and only format specified so far, and this will halt the machine with the execode stored in register specified by X. Now for this new instruction set architecture, everything will be built for the computer architecture. A simple make would do to show you that once this is built, a change to the instruction set architecture can be rebuilt much faster. I want to time this. Now we can double check. Second make should tell us that nothing needs to be rebuilt. The interface for input-output has just 2 functions, one for reading a character by default from the standard input and writing to the standard output. So what we will add is a function for reading a character into a register and printing a character that was stored previously in a register. We will restrict in the beginning ourselves to ASCII characters. That means 7 bits are actually sufficient for representing every printable ASCII character, or actually every ASCII character defined. And that means an additional bit can be used for encoding things like end of file. So for keeping this simple, that we just have to deal actually with 8 bits, I will realize these 2 instructions so that I'm just cutting them off, that I'm truncating them to 8 bits. And for that I use this bitwise AND operator from C. So with this opcode, we want to set a register, so set register. The value that we want to write into this register comes from the keyboard, a character that we read in. It's ASCII code. So rechar, truncate it to the 8 least significant bits with this bit mask. And we want to store that in the register specified by X. And here we want to write something to the keyboard. So ULM printchar. Now I have to specify a bit pattern encoding some character. This is the bit pattern from register X, so rec_val X, and this bit pattern gets truncated to the 8 least significant bits. And now let's rebuild this and also time. Okay, that's it. Now, as an example, I want to basically write a program here like cat, called without any arguments. Then you can type in something and hit return, then it prints these characters. And so this is a German hello world. And once you type Control D, this indicates end of file. The program terminates. And for that, you have to read characters, print characters until the character that was read in is this end of file specifier, which is not actually an ASCII character. So this is, I think, a good example for showing you everything. Now, in the beginning, I will just start with a simple program. Usually I would store them in the subdirectory belonging to this architecture. Actually, I can do this. And let's call this cat. And initially, I will just use, let's say, a few instructions to read 3 characters and print them. So I will read a character, print it, read the character, print it, and so on. So first I read a character into register 1. So these 2 bytes and instructions are actually not used. Then I print it. And this I want to do, let's say, 3 times. And then I want to exit with exit code 0. So this would do the job for 3 characters. Now we can run this, and I will first run this in the command line version of the computer architecture. So I probably should resize this so that you can read the path names. That I could type in more than 3 characters. Then you see it's just printing the first 3 characters. Now here it's actually hard to see what the program actually did. So let's run it in a debugger so that we actually see what's happening inside of ULM when we run this program. Now, this window becomes important. I can type in here something on the keyboard, and then you see that keyboard is buffering the input. After you hit return, it gets copied into a buffer, and this buffer can now be used for input. If the program reads some input, it will read it from this buffer, and if this buffer would be empty, the program would pause until some input would be available. Now you can step through this program instruction by instruction with Control S. You see 1 character was consumed and is now in register 1. Now this character gets printed, so you basically see what happened on the command line. And now the program terminates. Now for realizing this jump instructions, you will see that the control unit is responsible for the sequential execution of the program, and these 2 registers here are playing a particular role in that. In the debugger, you saw that the control unit has 2 registers. One of them is called IP, which is short for instruction pointer. I borrowed this name from the Intel architecture. On other architectures, it's also called, for example, program counter. The purpose of this register is that it's pointing to the next instruction in memory. And by default, the ULM will initialize this register with the 0-bit pattern. So that means by default, the first instruction that gets carried out when you run a program is the instruction at address 0. Because the ULM has a 64-bit virtual memory space, that's the size for this register, of course. The other register is called IR, which stands for instruction register. And because the ULM has 32-bit instructions, that's the size for this register. Now, to understand how this sequential execution of a program is defined by the ULM and realized, you have to know that each instruction is actually carried out in 4 sub-steps. I call this 4 stages. And after these 4 stages are completed, they get repeated. So that's why you have this cycle. In the first stage, where also the program execution starts with the first instruction, the instruction gets loaded from memory into the CPU. So it's a fetch instruction. And from the address stored in the instruction pointer, 4 bytes are copied into the instruction register. There it gets decoded. That means there is a lookup what instruction in your instruction set should actually be executed. And this actually happens in stage C. There, the microcode that you specified in your instruction set gets executed. After that, usually the instruction pointer gets incremented by the ULM architecture by 4. That means usually the next instruction that would be then in stage A, be executed, would come next in memory. But you can change that, because this increment by 4 only happens if your instruction, your microcode, did not write to the instruction pointer. So by using microcode that writes to the instruction pointer, you can change this default behavior that the next instruction comes in memory next. And I will show you that in the demo, where I first implement an unconditional jump and then also a conditional jump. For this jump instruction, I need first a new format for an instruction, and I will call this J26. And the upfield is as before. But now, as an operand, I want to use the remaining bits for specifying how many instructions to jump forward or backward. And this field I will call XYZ. And here I will use the specification J for jump offset. And it will use 24 bits. Now recall that every instruction has 4 bytes. That means if I want to jump forward or backward, I first of all want to use a signed integer. And such a signed integer would then always be a multiple of 4. And that would mean the bit pattern of this field used for specifying how many instructions I want to jump forward or backward always would end with 2 least significant bits that are 0. And that, of course, would be a waste. So the micro instruction will always use the bit pattern that you specify and will multiply it with 4. So effectively, you have 26 bits available to specify how many instructions you want to jump forward or backward. And now the instruction will get this opcode with J26 as format field. And this micro instruction from the control unit is called unconditional relative jump, or short rel jump, and XYZ is used as this special signed integer. Now let's rebuild this computer architecture and change the program so that we can take use of this in our cat program. Now I want to change the program such that it's reading a character into register 1, then printing it from register 1, and then jumps back to the read instruction. So I will not need the following 5 lines. After that I want to jump, so I use Xcode 04. Now also try what would happen if you would use this. Then you have an infinite loop, because the instruction then would jump to itself. We will also have an infinite loop when we jump back always 2 instructions. With that I would jump back 1 instruction. With that I jump back 2 instructions. So of course it will never terminate, so I don't need a halt instruction. Now let's see how this works out. I use the command line version of the computer architecture, and now I run our cat program, and I can type in hello, type return, then it goes into the buffer. From there actually something can be read and gets printed, then Welt, and now the only problem is that this never terminates, so I have to use Ctrl C. Now let me also run this in the debugger, then I can show you how we can detect a condition. Based on that, we could not jump back. And the condition, of course, should be that the user typed in Control D, as you usually would expect on Unix. So let's say I type in hello or German hello, and then Control D and put this into the buffer. Then we step through the program. Then you see here the characters that are copied into this register one, the ASCII characters, and then the Control D generates this bit pattern, which is not an ASCII character because all 8 bits are used. And this, of course, would be a -1 if we would interpret it as a signed character, or 255 if we interpret it as an unsigned character. And this will give us the condition. We will subtract from this register this bit pattern, and this would give us a 0 flag equal 1. And based on that condition, the jump should not be applied. So we only jump back if the bit pattern is different from FF in hex. So we need a instruction for subtracting a bit pattern from a register. So I will use first of all this format from before, then the subtractor, and I want to subtract the bit pattern from the instruction stored in the instruction, the immediate value, from the bit pattern stored in register Y. And the result should be stored in register Z. And then I also need a conditional jump. For that I will copy this here and modify it a bit. First of all, the opcode to hex 06, and then I changed this here, the instruction, into a conditional relative jump, and this expects 2 parameters. The first one is a condition, under what condition the jump should be carried out, and the second, the offset. So the condition is that the difference between 2 bit patterns is not 0. So I will check the 0 flag. So from the status register, I want to check whether the 0 flag is not 1. So it's 0. That means the bit patterns were not the same. And that's it. Now with that, I can recompile everything, or what is actually needed, and change the program. So we first subtract a bit pattern, namely FF, from register 01, and the result I store in register 0, because I don't need the result, I just need the status flags. And then I check whether we actually should jump back, and in that case we jump back now 3 instructions, and that means I'm having here FD. So if the 0 flag is false, then Control D was not typed in and we jump back, and otherwise we just continue with the next instruction, and this will halt the program. Now this will basically do the job. There will be a smaller thing that might to be fixed, but let's see. So I can now type in Hallo, Welt, and now with Control D it should stop. But then you see here this unnice character, which is not an ASCII character, obviously. That's the Control D. We somehow should change the program in a way that we first check if Control D was typed in, and only if Control D was not typed in, it actually should print. So I will introduce a new instruction which jumps in case of the 0 bit being 1. So for that I copy that, change that into opcode hex 07, change the condition to the 0 bit was set. Then I recompile, of course, and change the program. Now I first read in this character, Then I subtract this bit pattern from register 1. Then I will check if the 0 flag is set. In that case, I will jump forward to the halt instruction. Currently, that would mean 1, 2, 3 instruction forward. But you will see in general, you first have to figure out how many instructions are actually needed. Maybe you have to insert here a few instructions, then this might change. So this is something that we, without using assembly, have to fill out later. And so I come back to that later. Then I will print the character if I haven't jumped to the halt instruction, and then I will always jump back to the read instruction. So I need here an unconditional jump, and this should jump back 1, 2, 3, 4 instructions. So I have to change this into a C. Okay, so in this case, no new instruction was needed. Now I know that here I actually have to jump forward 3 instructions. Okay, so that's it. And now let's see. I type in something, I type in a bit more, and now I type in Control D, and program terminates without printing this enter file or this not printable character. In the demo, I explained with words that with this unconditional jump instruction, for example, you can jump forward a few instructions or backward a few instructions. And because each instruction is 4 bytes, we actually jump a multiple of 4 forward or backward. And the advantage of that we not store the distance in bytes in the instruction, but the number of instructions was that we can use 2 additional bits. Now formally I can describe exactly the same as follows. That this operand field is used as a signed integer, it gets multiplied by 4, and this gets added to the instruction pointer. And in the same way I also can describe all the functions for the control unit on the website. Actually there is just one function left that wasn't shown in the demo, the so-called absolute jump function, which gets used later for the function calls. With this function you can actually jump to a particular 64-bit address, and this instruction also will store the return address in a provided register. We will deal with that in some upcoming sessions, so I will just provide you this information so that you're having the feeling all things are covered, but the applications will come later. In the demo, I also just described in words my idea, my algorithm that I had in mind for implementing this cat command. And then in this first version, I made this obvious mistake that I was printing the end of file character, which is a not printable character. And I just said, stupid me, I should first have checked. And of course, this is something that works, such trial and error approach for very small problems like in this case. But we have to find, first of all, a more formal way to describe what the program is actually doing, so that we have a way to describe the algorithm without looking too close to the implementation, make it more readable for us. And then the second step, of course, would be to start with an algorithm, think about the algorithm first, and when we are sure that it's correct, start the implementation. And then there should be a straightforward way to go from algorithm to implementation. Now, the first step is to do the opposite, to go from the implementation to a readable description. And you see this here in this flowchart. This describes this second version for the cat command. And in this flowchart, you see, for example, that each box represents exactly one instruction, for example, for reading, printing, and halting the program. And this diamond shaped objects are jumps. If it's an empty shape, then it's an unconditional jump, also realized with one instruction only. And if you have a condition in it, then it's a conditional jump. Now you can, of course, try to describe this first version and then see that in this flowchart description, it's much more obvious what is actually going wrong. And later we will use this for developing a more complex program, the Hello World program.